I wanted to do a couple of problems today, including with series parallel networks and also with internal resistance. But let us start from this one, from a past exam that has a potentiometer. Okay, state Kirchhoff's first law, right? It means that the sum of the currents the sum of the currents that go in a node or junction is equal to the sum of the currents that go out of this junction. Okay, right. There is always something like a definition at the beginning with 1 mark. Now, let us see, this is the main problem. A potentiometer, this is the potentiometer, is connected to a battery of EMF 9.6 volts and negligible internal resistance. The maximum resistance of the potentiometer is 800 ohms. So all of this resistance is 800 ohms. A resistor R is of resistance 400 ohms is connected between the slider and X of the potentiometer. So here is the resistor for 400 ohms. State the potential difference across resistor R, that means this one, when the slider is positioned at end X of the potentiometer. In other words, when this slider here is actually here, when the slider is there, the X, what will be the potential difference across what one? Say the potential difference across resistor R. Okay, what is the potential difference across the resistor R when? Yeah, you know, when the slider is at position X, is as if this circuit looks like that. Okay, here we have the battery. We have the resistance R there, the 400 ohms, and the 800 ohms of the potentiometer is outside this this section here. So this circuit, in other words, is equivalent to this circuit, just to see that this resistor of 400 ohms is not part of this part. So this part, actually, which is across the resistor R, is actually connected with just a piece of wire. So let me fix this. This resistor R in this scenario here, as you can see, because of this wire here, is actually short-circuited. So when a resistor is short-circuited, it's as if this point and this point are actually one and the same point, as if you take the two and you put them together. It's like this, is as if this resistor is eliminated from the circuit, from this circuit here. You need to imagine that these 2 points are actually on top of one another. This is short-circuited. So what is the potential difference across a short-circuited resistor? It's 0, isn't it? So the answer to our first question here, find the potential difference across resistor R when the slider is positioned at X, the potential difference here is 0. Next, if the slider now is at position Y, we take the slider now from X, let's remove it from X, and we place them at the other end. So the slider now is there. Here is the slider, which means, let's redraw our circuit. It's nice to redraw your circuits, especially when you're beginners, and don't be lazy, because it can save your life sometimes. So now, because the slider has gone there, it means that all this resistance of 800 is included parallel to this resistor R. So it's like having all this resistance of 800 ohms connected across resistor R. I hope you understand this drawing. This is now equivalent to this one. So what we have here now, it's like having 2 resistors here in parallel, one of 800 ohms, the other is 400 ohms. And what do we need to find? We need to find the potential difference again across resistor R. In other words, the potential difference across resistor R, which is the same as the potential difference across the A, isn't it? Because this branch has two resistors in parallel. Obviously, they share a common potential difference across their ends. And this is 9.6 volts. So obviously the potential difference across these 2 points is 9.6 volts because there's no internal resistance. So our answer here is that the potential difference is 9.6 volts across resistor R. Remember, these 2 points and these 2 points have the same potential difference, isn't it? All right, I hope you understand that. If there are problems, you can send me a message because I can see your messages. All right, I have this box with your messages. All right, so this is actually quite an easy problem that we could do it in like 1 minute, we could finish it. All right, so I just need you to understand what happens with this slider, and especially I wonder if you understand well, if you have ever come across the concept of short circuit, because they love to have a question that involves short circuits in the problems, okay? Even if it's not explicit. Let us see another problem. I think that again there is a case with a short circuit, which is this problem. It's from another past exam paper. All right, here it is. Which exam paper is that? I don't know. This is from 2016. Yeah, anyway. Let's see this problem. We have now define it like that. B, let's start from here. A battery of EMF 14 volts, here it is, and negligible again internal resistance is connected to a resistor network, which is shown in this diagram. R1 and R2 are fixed, R1 and R2, and they have a resistance of 6 ohms and 12 ohms respectively, and R3 is a variable resistor, and as we can see in the diagram, it can take values from 0 up to 24 ohms, but nevertheless, it's a variable resistor. So let's see what's going on. Calculate the current in the battery. In other words, they want the main current here. Let's call it I, or maybe I total perhaps. Calculate the current in the battery when the resistance of R3 is set at 0. There we have it again. Oh, switch S is closed. Okay, so this is closed. All right, closed. Okay, and find the current when the resistance R3 is set at 0. 0. You see that there is another short circuit. It's like having a piece of wire here connected across resistor R2. Let's redraw this diagram. Here's the battery. Here is the resistor R1, and here is, look at this R2. This R2, R1, and now, because this is set to 0, means that there's no resistance in this branch. It's like having a piece of wire with no resistance connected across resistor R2. And I want you to understand this very well, and please let me know, send a message, okay? So if this is just a plain piece of wire with no resistance, this resistor R2 is short-circuited. A piece of wire with no resistance across 2 points of a circuit is a short circuit. And if this is if this resistor is short-circuited, it's as if it has been eliminated from the circuit. And I'm going to redraw this diagram so that you understand what I'm saying when I say that it is as if those 2 points are on top of one another. So that would be the R1. And the other one, look at this, is like those 2 points. I take those 2 and I put them one on top of the other. And what is there? It's like this resistor R2 has been left out of the circuit, has been eliminated. And the circuit continues there with whatever else is there. Here's the battery. So it's like having this scenario. This is exactly the same like this one, and this is the same like this one. So you see this resistor there is like as if it does not exist. It's not, has been eliminated, has been short-circuited, which means it's like having this scenario. Hold it in. It's like having this story here. In other words, we have a circuit with just one resistance, the R1, which is 6 ohms. And this is 14 volts. And what must we find now? Calculate the current in the battery. Okay, so we have the current in this circuit, which contains just one resistor, 6 ohms. And obviously we apply Ohm's law. V, the current is V over R. What is V? It's this EMF of the battery, which is 14 volts. And the resistance in the circuit, which is just the 6 ohms. Yeah. All right, and this is what is 2,3 amperes. Eh? My calculations there. Yeah, 2,3 amperes. So this is the current they are looking for. So we say here 2,3 amperes. Now, this is the story if this R3 is set to be 0, okay, which was a short circuiting this resistor R2. Now, this resistor is set at its maximum value, which is 24 ohms. So now we have a resistance here. It's not anymore 0. So let us, sorry, we need some space here. It is like having here a resistance in parallel to the R2. Okay. Pen, please. Thank you. All right, so here's the R2. Now we have a resistor of 24 ohms across the resistor R2. So now this is said to be 24 ohms. This is the R3. Eh? Okay, so what's happening now? We need again to calculate the current. Now we have a circuit which it's a combination series parallel network here. This is still 14 volts. Okay, for us, the first thing when we need to find something in a complex circuit, the first thing is to get rid of the parallel connection, the parallel branches. Okay, so let us get rid of that and replace it with their equivalent resistance. So R2, what is R2? Is 12 ohms. 12 ohms. All right. So we need to find the equivalent of this combination so that once we have the equivalent, we can find the current in the circuit. So 1 over R, let's call it parallel, the equivalent resistance of this branch, that is. We apply the famous formula for parallel resistors. 1 over R2 plus 1 over, what is this, R3, and this is 1 over 12 plus 1 over 24, and let's work here. That will be 2 plus 1 divided by 24. I hope this is correct. This is 3 over 24, which means the parallel resistor will be 24 over 3. 24 over 3, which is 8 ohms. I hope 8 ohms. All right. So the equivalent resistance of those two, in other words, we found is 8 ohms. So now, okay, this is 6. Okay. All right. I'm trying to fix the significant figures. Nevertheless, here it is. Let's write it with 2 significant figures. All right, so this is 8 ohms. Okay, all this, this is equivalent to 8 ohms. We can even draw it as 8 ohms so that it looks nicer to the eye, more simple. And this can be our equivalent resistance of 8 ohms. Okay, 8,0. Okay, I'm not writing all the zeros. All right, so now what is the total resistance here in this circuit? It's 6 plus 8 is 14 ohms. 14 ohms, and the battery is 12 volts. We can apply Ohm's law to the whole circuit here. Let's right here. So the total current then is V total, which is V, divided by the total resistance, which is 6 plus 8, which is 14 ohms. I have the value there. Let's put the value there. The potential difference across the two resistors. This is what, 12, eh? Oh, sorry, 14, not 12. 14 volts. And 14 divided by 14, the current will be 1 ohm. So the total current in this case, when this resistor has its maximum value of 24 ohms, we found is 1 ampere. Here's the ampere. Okay, so this is 1, okay, in 2 significant figures. All right. Okay, so this is the answer here. What lessons do we get from this problem? Would we expect the current in the second case to be smaller than the current when this resistor was omitted from the circuit because it was short-circuited? Yes, of course, because now with this parallel connection here in series to the resistor R1, we have extra resistance in our circuit, isn't it? We have this resistor R1 plus some other resistance, which we found actually was 8 ohms. It was not, it's quite big. Yeah? So yes, we would have expected to find the current which was smaller than the first current that we found of 2.3 amperes. Okay. All right, there are many things to say about resistors in series and in parallel. I want you to tell me how easy you find these problems with which contain resistors in complex networks. Okay, let's do another one until, I don't know if you write a message, if you send me a message, but in the meantime, let us, I have drawn here a diagram, hand-drawn diagram, as you can see from the shaky lines, that because it contains internal resistance. Okay, let's do a problem that involves internal resistance. So we have, look at this. We have this circuit here. It has a number of resistors. It has this parallel branch with two resistors that one is called M, the other is called N, and we're given the value of this N resistor, which is 2 ohms. There's another resistor there, Y, and these are connected now across a battery, which with internal resistance, there is an internal resistance here, and we are told that the terminal potential difference across the battery is 14 volts. Okay, be careful. This 14 volts includes the potential drop across the internal resistance. So it's across the whole battery, across the terminals of the battery, the real terminals of the battery. That's why we call it the potential difference, the terminal difference across the battery. What else do we know? So we know these 14 volts. We also we see that there are two ammeters connected. One is connected here, which reads the current in the main branch, the current in the battery, in other words, which is 2 amperes and it's given. And we also have another ammeter here connected. Look where it is connected. It's in the parallel branch. In other words, this one, and it's 1 ampere, it's given. This 1 ampere obviously is the current that is in this resistor M, called M, but we don't know its value. So the first question here says, we ask, compare the value of resistors M and N. So the first question says, compare the values of the resistances of these resistors M and N. How do they compare those two resistors from this data that we have? Okay, this is not a difficult question because we are given this current 1 ampere and we are given also this current of 2 amperes. This is a total current, okay? Right. If we can apply actually first the first of Kirchhoff's laws for this node here, for this junction, or that one, the same thing. Look at this. Let's have these wires here separately so that we can see it clearly. what currents do we have meeting at this junction? We have this A2, which is called A2, which obviously, look at this, should be in this direction. Let's call it IM, because this is actually the current that goes through in resistor M. So let's call it IM. And let's call this the current IN. And let's call this the total current, okay? Why do I have this direction? Because look at this positive terminal of the battery. Obviously, this total current is in this direction, isn't it? All right, so what do we have here? We have this total current entering the junction here, and we have this current IM leaving the junction, and we also have this current here in the other resistor also leaving. And so if we apply Kirchhoff's first rule, the sum of the in currents must be equal to the sum of the out currents. So the sum of the in currents equal to the sum of the out currents. The in current is the I total. And this is equal to the IM plus the IN. And we know that this is 2 amperes. And we know that this is 1 ampere. 1 ampere, value please. 1 ampere. And what must be this current then, which is unknown? Obviously, it must be also 1 ampere, isn't it? I'm just going to write it straight away. That's also 1 ampere. And what do we have there? We have that these two currents are equal. If these two currents are equal, what does it tell us about the values of those two resistors? Obviously, these two resistors must be equal, which means that the resistor M must have a resistance which is equal to the resistance of the resistor N, which is 2 ohms, isn't it? So there we have our answer. It's not a difficult, so that was not a difficult question. What is our answer? The resistance of the two is are equal. They are equal to 2 ohms. Why? Because if this current is 1 ampere and the total current is 2 amperes, we know that this must also be 1 ampere. So 1 ampere here, 1 ampere there. Obviously, this have the same resistance. All right. All right. Okay, next question. What do we have now? And if the next question, let's read it here. B. What is it? If the EMF of the battery is 17 volts, the EMF is 17 volts. So this, in other words, is 17 volts, the EMF of this battery. Calculate the R, the internal resistance of the source of the battery. That's also an easy question. It's nothing special because, come on, what is this? Okay, all right. So to find, what do we have here? We know that the potential difference across the terminals is 14 volts, and the EMF now is 17. Which means the potential difference across the internal resistance is 17 minus 14. This must be 3 volts, isn't it? 17 minus 14 is 3. Check my calculations. I can do a mistake in the most easy numbers. All right. So we know that the potential difference across the resistor, the internal resistance R, is 3 volts. If I need to apply Ohm's law to find the the value of R. So R, if I R is V over I. What is this V? Is the potential difference across the internal resistance. Let's call it VR to know that we're talking about the potential difference across the internal resistance only. And what is the current in the internal resistance? Is the same current that in the battery, is the current in this main branch of the circuit, isn't it? So it's 2 amperes, we know it. So this is 2 amperes, we know it. Okay, so if we add the values here, the V across the internal resistance is 3 volts. The current is 2 amperes. And what is the value here? 3 divided by 2, it's 1,5 ohms. So this is the value of the internal resistance of this battery. Okay, all right. And what else do we ask here? There is a third question here, C, say the C. Calculate the potential difference across N. Okay, we need to find the potential difference across N. In other words, we need to find the potential difference across this parallel branch. Okay, when we have a parallel branch, what do we do to facilitate our lives, especially now that we know the resistors? We need to find the equivalent resistance here. Okay, so let's say this, the equivalent resistance of this parallel branch. Let's write it as R parallel. How do we find this? It's 1 over Rm plus 1 over Rn. That will be this equivalent resistance here. And, oh, but these two are equal. Okay, even without calculations, I know that the equivalent resistance is half of one of them. So if we do the calculations here, we're going to find that R parallel is 1 ohm. I don't know if you know if you're familiar with these little tricks to find resistors in parallel branches easier. But if we have two resistors in parallel and they have the exact same value, then their equivalent resistance, if they are two, their equivalent resistance is half of the value of 1. So if here we have 2 ohms, half of 2 is 1 ohm. So this is the equivalent resistance is 1 ohm. If we don't know any tricks of the trade, then we just do the calculations. You see, we're going to find 1 ohm. So we know that the potential difference, sorry, the equivalent resistance here is 1 ohm. Okay, if this is 1 ohm, then if I apply Ohm's law across this branch now, then what do I need to find? I forget. Calculate potential difference. Okay, potential difference V across the, let's call it across the resistor N. This is I times, in other words, the current here, the total current that goes, that is in the equivalent resistance of the two parallel resistors, times what? The resistance of the parallel connection. And this is now 2 amperes, because the total current is 2 amperes, times 1 ohm, because we just found that this is 1 ohm, and this is 2 volts. So there is our answer, the potential difference across this parallel connection. They told us across the resistor R, across resistor N. We found this is 2 volts. 2 volts. All right. Okay. Guys, I want to ask you a question. Say that we have a bulb connected across some battery, okay? And say, for argument's sake, that the current here is 1 ampere, okay? If we connect a second bulb across, a second identical bulb across the same bulb and the same identical battery, I want you to tell me what is this current here in this circuit. And then I want you to think of this problem when we connect another bulb in parallel to this first bulb. All these are identical bulbs, all the batteries are identical. I want you to tell me what is this current in this parallel branch and what is this current in the series branch. I want you to think of it. I need you to tell me what are these currents and also these currents in these individual bulbs. I want you to tell me for next week, because if you answer this question correctly, it determines what we're going to do next, okay? So, all right, I hope you are following here, and please let me know how easy you find circuits with complex branches of resistors and internal resistances and so on, okay? So, So remember that you can also tell me what you want us to do next, all right? Because otherwise I'll have to choose again. But nevertheless, for next week, please try to answer this question for me, and we can discuss it when we come here, all right? So let's call it a day now because it's 12 o'clock. So guys, have a great week, and see you next week, all right? Bye.